In this video, I discuss some concepts related with the sphere. Let's begin by writing the equation of the sphere, and then I'll discuss the tangent plane and the tangent lines. So in order to write down the equation of the sphere, we should know its definition. I will write down a very brief definition. So the locus of points which are at a fixed distance from a fixed point. So such a locus will be called as a sphere. The fixed distance is called as a radius, and the fixed point is called as the center. So in this diagram, C denotes the center. Let us say that the coordinates of C are A, B and C. I take a point on the locus, any general point P on the locus with coordinates X, Y and Z. And now using the description over here, I will write down an equation. So using the distance formula, so what I do is I calculate the distance between the point P and C, and as per the requirement over here, that should be equal to the radius. So this distance, let's say, is R, the radius. So x minus a square plus y minus b square plus z minus c square equal to r square. P is a variable point. So x, y and z are variables. And if the coordinates satisfy this, what we have got is the equation of a sphere. Now, how does this compare with a general second degree equation in three unknowns? A general second degree equation in three unknowns will look like so. Okay, so that is how a general second degree equation would look like. The question which I want to ask is, when would such an equation represent a sphere? So let us see what are the commonalities between these two equations. Now, if you expand the left hand side, if you expand the brackets on the left hand side, it is clear that terms of this kind, xy, yz and zx, are not appearing. So alpha, beta and gamma should be equal to 0. So such things should not exist. So mixed terms will not be there. Okay. Now, is this going to represent the equation of a sphere for all possible values u, v and w and d? Let's check this. Now, why are we doing all this? The reason is that, if you go back to the two-dimensional setting, the general second degree equation is related to a very, very specific kind of geometry. All right. The general second degree equation represents a conic. And what are the conics? A pair of lines, circle, ellipse, parabola, hyperbola. These are the conics. So there's a question that if you have a second degree equation in three unknowns, what does it represent? So the study of the second degree quadratic, the study of the quadratic in three unknowns, the general quadratic in three unknowns is of interest to some people, and there is some connection between the algebra and the geometry. So as of now, we are not going to go into the details of that, but then you get a slight glimpse from here that when you work with the second degree general equation, and if you wanted to represent a sphere, certainly these terms should not be there. Okay. Now let us compare these two equations a little more carefully and try to see what should be the condition on u, v, w and d to represent a sphere. So the left hand side is a certain sum of squares. I will try to write the left hand side of this equation also in a similar fashion. So what I have is x plus u square plus y plus v square plus z plus w square equal to u square plus v square plus w square minus d. So what I've done is I've taken this d on the other side and added u square, v square and w square on both the sides and completed the square. So you can just check that. Now if you compare it with this equation, this entity cannot be negative, and therefore one of the conditions to be imposed on u, v, w and d is that this expression should not be negative. Okay, if this let me denote this equation by star. If u square plus v square plus w square minus d is greater than or equal to 0, then star represents a sphere with center and radius okay. All right, so this was the discussion about the equation of the sphere. Now let us move on to the tangent plane. Before I move on to the discussion of the tangent plane, I just wish to make a remark and also set up a convention, a notation. The expression, okay, so if you just open this up, what we get is the expression which I just erased. I will write it down and give it a name. Sxyz equal to 0 where Sxyz is equal to x square plus y square plus z square plus 2ux plus 2vy plus 2wz plus d. So I'm going to call this expression as S. So I'll be writing it as Sxyz equal to 0, and if the context is clear, or simply S equal to 0 if the context is clear. Alright, so S equal to 0 will represent a sphere if this condition is satisfied. What is the purpose of this notation? Now, if you're dealing with level surfaces, which is going to be the case if you're going to study vector calculus,